Okay, thank you. No? Oh, okay. Oh, okay. Okay, so first of all, I would like to thank the organizer, especially Julia, for inviting me to this conference. This work is in collaboration with my postdoc, and also with Joe, who is sitting on the audience. So, and this is the outline of my talk. So, because, as you know, many kick rotor without spin is now a well-established subject. So, many people of this conference take a very fundamental contribution to this subject, and therefore I will give you only the minimal introduction which is related to my work. And then in the second part of my talk, I will introduce you our results. So I will show you that when we add a spin degree of freedom to the usual kick rotor, and then a phenomena which is phenomenologically analogous and mathematically equivalent to integer quantum Hall effect will arise. I will show you I will summarize the results and present the analytical theory, and I will also show you some numerical confirmation, and finally I will discuss with you. So this result actually is of some chaos origin, and then I hope that I will have time to discuss with you the third part. Actually, I will show you that this result, although it is a one-dimensional, one-particle problem, it has a very close relation to the famous Haldane conjecture for quantum antiferromagnetic chain. And this conjecture this connection is recently important to me because it helped me to understand many puzzling questions, and it is also bringing me new interesting results. So let me start from the first part. So as Felix already mentioned in a previous talk, so the kick rotor Hamiltonian is extremely simple. It basically includes two parts: the free rotation part and the cosine potential part, which is switched on only in the integer time. So after some rescaling, we know that this system is controlled by only two parameters. One is the Planck's quantum, and the other one is the nonlinear parameter. And the question which we would like to address is simple. So we let the system evolve unitarily according to this Hamiltonian and find how the kinetic energy grows in the course of time. Evolves in the course of time. So in a simplest case where Planck's quantum is 0, this was thoroughly understood by Chirikov in the 60s. And I would not like to go into details. Basically, Chirikov realized that for standard map of classical kick rotor, the system will undergo a transition from KM regime to the strong chaotic regime. So, and moreover, it is possible to calculate, to show that in a long time, in a strongly chaotic regime, the kinetic energy will grow linearly, and this is nothing but the classical diffusion in the angular momentum space. So, and because this talk has really close connection to condensed matter, it may be possible to think about something in the language of condensed matter. In this regime, because the motion is confined in the angular momentum space, is something like a classical insulator. And in this part, because when k is large enough, we know the system is deconfined in the angular momentum space, and also the kinetic energy grows linearly in time. This is something similar to the normal method. Now, what is interesting, what happens if the Planck quantum is non-zero? And this is something I would like to address in the remaining of my talk. And as we know, so this was first studied by Giulio and Felix and his company in 1979. They basically found in a long time the classical motion will be totally suppressed by the quantum interference. And as a result, the kinetic energy will saturate in long time, and this is nowadays called dynamic localization. So, and later on, Schwinger-Fishman and his company managed to map the Bloch theory of kick rotor into a time-binding like Anderson-like model. Basically, it's described by this equation. Now, the detail is not so important. What is important is that it includes two terms. The second term is something similar to the hopping term, which is due to the kicking. And the first term is like an on-site potential, which is similar to the disorders. Why? Because if the Planck constant is a generic irrational number of this ratio, then we find that if n slightly change, then this time value will change dramatically, and this is like a random potential. And then this led them to conjecture that under dynamic localization actually is something like an Anderson localization in energy space, although there is no real disorder at all. But of course, as we know, the story is not so simple as this conjecture gives us. You know, Felix and Shapiransky know very well that actually the results is very sensitive to the value of Planck of this ratio. For example, a long time ago, they consider this ratio to be rational. We Q small enough, then instead of getting dynamic localization in a long time, we find that the kinetic energy will grow quadratically, and this is what they call quantum resonance. So what's the physical become? Basically, it means that in the presence of this ratio, so the Floquet operator has the translational symmetry in the angular momentum space. As a result, the system is more or less like a one-dimensional perfect crystal, and there is no dissipation. For this reason, one may call it supermetal. So, and therefore, so we see that the standard quantum kick rotor can simulate many condensed matter in one-dimensional, like a disordered solid or perfect crystal. So the question is that what happens beyond 1D? So the recipe was given by Giulio and Guarneri and Shapiransky in 1989. The idea simply is as following. So let's modulate the potential. Let's introduce D minus 1 additional frequencies to modulate the kicking potential. And as a result, they show that this system is exactly equivalent to D-dimensional periodical system. So in this case, by using this trick, it is possible to use the one-dimensional quasi-periodic kick rotor to simulate D-dimensional physics. So indeed, about 10 years ago, in a French school, so they managed to realize this potential, use this trick to realize this potential, this kick rotor, and they discover the Anderson transition in the quantum kick rotor, and furthermore, they measure critical exponent experimentally, and which is quite close to the simulation results. So, but this result is again for irrational values of this ratio. So, what happens if this value is rational? So, it turns out that all the Anderson insulator will be turned into a supermetal, namely the kinetic energy will grow quadratically in long time. And then as a result, all the Anderson metal insulator transition is turned into metal supermetal transition. And this was first predicted analytically by the supersymmetry field theory, and later on by large scale and with high-weight analytical simulations. So, and basically, this did bring me to the end of my short summary. So I hope I convinced you that, and even for Kick-a-Rotor without spin degree of freedom, by simply tuning Planck's quantum, we can see there are a lot of interesting phenomena. But nevertheless, these phenomena are associated with the restoration or breaking of the translational symmetry in the angular momentum space. Now, in the remaining of my talk, I will focus on this question. So, if I introduce the spin degree of freedom to the Kick-a-Rotor, what happens? So, and this is the second part of my talk. So, let me start from the formulation of the problem and then summarize the results. So, this is the Hamiltonian. More or less is the same as the usual Kick-a-Rotor, but quasi-periodic Kick-a-Rotor, but there are essential differences. First of all, the kicking potential will couple the spin. Okay, so first of all, the particle has 1/2 spin. And this kicking potential will couple the spin degree of freedom in the angular position. And then this kicking potential is modulated by one additional frequency, similar to what Julio and his company did a long time ago. And this omega theta is incommensurate with 2 pi. Now, physically, it means that upon kicking, the angular momentum of the particle will have a sudden jump as usual. However, it is important that the spin degree of freedom, that the spin will be also flipped simultaneously. So in this sense, it's something which is similar to the spin-orbit coupling. So and it turns out that, as I will show you, the details, the results which I will explain you later on, does not depend on the details of the potential up to some symmetry, okay, which is written here in this table. I will not like to explain the details why there is this symmetry, but what is important is that this symmetry will basically bring the system to the symmetry class A in the language of randomized theory. So in the question which I would like to address, more or less is the same as we usually Kick-a-Rotor. Namely, I will consider how the kinetic energy, the scaled kinetic energy grows, change in the course of time. So, and now I would like to tell you the results first. So first of all, let me remind you that in this case, I fix all the parameters except they are allowed the Planck quantum to change. So that is to say that in a microscope, for this microscopic model, so the system is controlled only by the single parameter, the Planck quantum, HE. Nevertheless, I will show you immediately, in the long time or microscopically, it turns out that the system, the physics of the system is controlled by 2 parameters. One is the asymptotic energy growth rate in long time. And the other one is that, as I will show you, it turns out that there is a hidden quantum number, which is actually the so-called quantized topological theta angle, which was first introduced by Tooth in a study of QCD long time ago. So, and now, let me summarize the result one by one. First of all, let's consider the energy growth rate in long time, which is relatively familiar with people in nonlinear dynamics. So in the horizontal axis is the inverse Planck quantum. This means that on the very right-hand side is something like in a deep semi-classical regime, and near the origin is like some deep quantum regime. And then it turns out that for almost all the Planck quantum, the energy growth rate in a long time will vanish. That is to say, it's something with more or less the same, phenomenologically the same as the Anderson insulator or dynamic localization in the sense of the standard quantum Kick-rotor. However, there is an infinite set of critical values. Exactly at the critical value, in a long time, the energy growth rate or diffusion coefficient will jump to some finite constant. And this means that actually we have a sequence of metallic phase, okay? Because the system is diffusive exactly at the critical point. And between the peaks, we have the insulating phase. Now, it turns out that this critical diffusion coefficient is order of unity, and then it's independent of the details of the potential and also independent of the critical points. So, moreover, if we go to the very deep semi-classical regime, it turns out that there is an interesting phenomenon in the critical points actually are equally spaced along this axis. So, and now this is basically this is the result of the analytical result of the energy growth rate a long time. So the question is that is the insulating phase is the same as the usual Anderson insulator, or namely something similar to the usual dynamic localization or not? The answer is no. It turns out that each insulating phase will be characterized by some integer. And then, if I go to the very deep quantum semi-classical regime, it turns out that there is a universal pattern in the following sense. Whenever I decrease the Planck quantum and go across the critical point, and this pattern will jump, this integer will jump precisely by unity. And as a result, I will have a staircase pattern. So in this quantum number, as I said already, and I will explain you later, it is of topological nature in the sense that it is actually quantized the topological theta angle. It is not so easy for me to explain in this moment, but I will show you later on. Now, if we compare, just make some naive comparison of this pattern to this famous result of integer quantum Hall effect, what happens? We realize that it is actually there is a one-to-one mapping. So the energy growth rate in a long time, we apply the law similar of the DC or longitudinal conductivity because in the integer quantum Hall effect, remember, so because in the process of magnetic field, so it is a conductivity tensor, and as a result, there is a DC or longitudinal conductivity and also the transverse or namely Hall conductivity. And this quantized quantum number, we apply the law similar of the quantized Hall conductivity. And the inverse Planck quantum, we apply the law of Haldane function, or in other words, so the Planck's quantum will apply the law of the magnetic field. Of course, question is that this is whether this is by accident or not. But before I say this, so it is important to realize that there is fundamental differences between this phenomena and the usual integer quantum Hall effect. Yeah? So, for example, in this case, there is no magnetic field, okay? So we just get the spin. And there is no electromagnetic response. And all the interesting phenomena is simply driven by Planck's quantum, as what we did for usual Kick-rotor long time ago. And later on, I will show you that this phenomena is actually of a strongly chaos origin. And now, you know, in a user kick load, in a user integer control effect, in order to have this staircase pattern, we need to have the integer feeding. And this is a result of the Pauli principle. It's a really important, which is a really basic many-body effect. But now here, we simply have a one-body system. We have only one particle. And then, you see, so this is a one-dimensional problem. It is far from equilibrium system. And as a result, it is really difficult to believe. It is really different from the usual integer control effect. Okay, and finally, for this system, we don't have any translational symmetry, and we don't have the adiabatic parameter cycle, and therefore it is not so easy. I mean, it's not clear to me whether one can formulate a theory similar to TKNN invented by Saulus Komoto and the company, and this is important. This is a foundation of the integer control effect without any disorders. Okay, it is not so easy, not clear to me whether it is possible to formulate or not. So, and then I don't really need to have an analytical theory to explain you how why it is topological and how this result come out, because we are still working really hard to try to figure out some transparent physical picture behind. But at this moment, we have only, to be honest, we have only analytical theory and numerical confirmation. So, and this brings me to the second part, to the brief introduction of the analytical theory. So I will sketch only the details, sketch only the analytical theory without going into too much details. And the first step is more or less the same as what Julian and his company did a long time ago. So for this quasi one-dimensional periodic system, because I have only one additional frequency, it is possible to map, follow the trick of Julia to map this system exactly into 2D periodic quantum dynamics. Okay, so and for this 2D dynamics, it's controlled by this Floquet operator U, and he basically split it into two parts. The first part is due to the kicking, and the second part is due to the free rotation at plus the incommensurate frequency. Okay. And then it is possible because we are interested in the kinetic energy, so it turns out that this kinetic energy can be exactly expressed in terms of this integral. Now, what is important is that we can express this kinetic energy in terms of this k omega. What is this k omega? And all the others actually are not important. And what is this k omega? And this k omega is actually something similar to the two-particle Green function in the condensed matter. He basically probes the interference between the advanced and retarded quantum amplitudes in a two-dimensional angular momentum space. Remember, because now in this 2D system we have two angular momentum. One is the real angular momentum, and the other one is canonical conjugate to the quasi-periodic driving. So, and basically, this is the details of the detailed definition of this two-particle Green function in terms of the, and this Green function can be expressed in terms of the Floquet operator. Now, it is very important that in this exact formula, including the integral over the U1 gauge group, over the U1 group. And this is intrinsic to the periodic driving, and this is crucial to what we will discuss later on. So, and then the whole story of the analytical theory is to try to calculate this two-particle Green function k omega. Once we have it, then we have the kinetic energy explicitly. And next step, we will introduce the standard trick of the supersymmetry and to namely to introduce a super vector and then express this k omega in terms of the integral over the super vector. In this stage, again, is quite standard. And now let me remind you again, in this k omega include an integral over the U1 group. And the next step is to perform the integral over the gauge group, U1 group. And then this can be done by using identity, Regulus identity discovered by Martin Semple a long time ago. And what is the important point is that after using this integral, we see some supersymmetry field theory will enter automatically, without any approximation. So that is to say, putting in another words, the integral over the U1 group is reduced into some function, some integral over some supersymmetric matrix. It is not important to understand the details of ZZ theta. What is important is that mathematically, this ZZ theta is a product of these two geometrical objects. And this is the two sphere. And this one is the upper surface of the Lobachevsky space. Okay? And this, if we would like to be slightly more mathematical, basically it means that the reduction after this identity, the integral over the U1 group is reduced into the integral over some symmetrical space. And this is the geometry of the coset space, of the symmetry space. Now, in the end of the story, we can express this this k omega in terms of the functional integral over the super vector field in the J field. And moreover, because it is quadratic in this poset, and therefore we can integrate out of this poset immediately, and as a result, this k omega is explicitly and rigorously expressed in terms of the functional integral over the supermetric field. And everything is controlled by this action. So now, the funny thing is the following. This J is, in principle, is off-diagonal in the angular, two-dimensional angular momentum space. What's the physical behind? It basically probes the corrective mode of the coherent motion of the quantum retarded in of the quantum amplitude, something like a diffusion of quantum corrections to the diffusion and whatsoever. Now, it turns out that if we consider really long time, this off-diagonal part will decayed, and this is called the so-called fast mode. In the presence of strong chaos, namely the system, the rotor will lose the correlation in the angular momentum, in the angular coordinate in short time. It turns out that these fast modes will be eliminated from the field theory, and as a result, it includes only this diagonal part. And as a result, these small modes will introduce a mapping from a two-dimensional angular momentum space to this target space. Now, the topology of this mapping turns out to be non-trivial, and it's characterized by this second homotopical group, which is given by this state. And this is the topology behind, the topological reason behind. And then it is possible, after this stage, one can perform the standard hydrodynamical expansion of the exact action of this. We perform the second order hydrodynamical approximation of this exact action. And as a result, this action will be given by this action. Right? Now, if we forget this term, what happens? It is nothing but the field theory described the 2D Anderson localization, which of course was also observed experimentally and also numerically for the kick rotor long time ago. So now we spin, we know there is this rotational term. Now, why it is topological? Because if we change the metric of the two-dimensional angular momentum space, it turns out that this term is invariant, and therefore it's of topological origin. Actually, in the literature, it's called topological theta term. And now, it is for this term, this action is controlled by two parameters. One is sigma, and the other one is sigma h. It depends on if we change, if we evaluate with the effective Planck quantum. Now, what is the physical meaning of these two coefficients? So first of all, it can be shown that this sigma has the following scaling. It's proportional to 1 over h bar square. And if you are familiar with the kick rotor, we know it is actually the short-hand diffusion coefficient. Okay? And then this term is proportional to inverse Planck quantum. Remember, what I told you a moment ago, this Planck quantum is more or less similar to the magnetic field. What is this? This is the classical Hall's law. Then, this is what I said a moment ago. And then what can we do with this? These two pair constants more or less describe the kick rotor dynamics only in the short time. But for a long time, we need to have something more. And this is to deal, what can we implement this something more? We need to use the renormalization group analysis. I would not like to explain the details, but let me just mention two things. This renormalization group analysis includes two steps. The first step is the prescription of the so-called background field formalism introduced by Provisky a long time ago. Basically, it means that it is possible to introduce kind of linear response to this system, to this field theory. Then we calculate the transport coefficient. This is the physical behind. And then, after this, we perform a perturbative and non-perturbative instanton analysis. As a result, I will come up with this two-parameter beta function Gabor equation. So this is the first equation is the normalization of the short time of the diffusion coefficient, and this is something like a renormalization of classical Hall conductivity. Now, what is interesting? The interesting thing is that on the right-hand side, it is periodic in this parameter, and it is the period of unity. And as a result, we see that this renormalization group flow is given by this one. This is exactly the result given by Manischky in 1983 when he tried to understand the integer quantum Hall effect system in the presence of very strong disorders. And this is something very different from what Solis did, because Solis only studied systems without any disorders, okay, and then come up with TKNN. But this is another thing. For Manischky is another thing. He considered another limit, which is in a very strong disorder limit. And this is exactly the same as what he studied for integer quantum Hall effect. Okay, so you see, it is not by accident. So basically, we will find that there are two critical points. There are two fixed points, and one is the insulating phase. So this blue dot, exactly at the insulating phase, as we expect, the conductivity, the diffusion coefficient will exactly normalize to 0, and then this topological theta angle will be renormalized to some integer n. This is why I said that this hidden integer is of topological origin. Basically, it's the quantization or renormalization of the topological theta angle. And then exactly at the critical point, we see that the diffusion coefficient is no longer 0 in a long time. it's given by some universal constant, which is 1/2, which is order of unity. So now, what happens if we decrease Planck quantum? We will see that the system will bypass the critical line one by one. And as a result, you will see that the hidden quantum number will jump one by one, and therefore we will have the staircase pattern, which I showed you a moment ago. Moreover, it is possible to estimate the critical energy growth rate, which is close to 0.44, and the critical exponent can be estimated, which is close to 2.75. So, and now let me provide you some numerical results. So first of all, we would like to choose this model, which was introduced by Binaka some time ago. And then let's check what happens if we consider a short time. So we see that no matter what kind of Planck quantum I have, so we always have the linear diffusion in short times. Moreover, the short time diffusion coefficient is an excellent agreement with numerical simulations. And then furthermore, we see that if we diagonalize the system for small size of angular momentum space, the level statistics will follow the Wigner Dyson of unitary type. So this is a perfectly chaotic system. Now we are ready to use this model to study what happens in a long time. It turns out that the results are totally different from what I showed you in previous slide. So according to the analytical theory, there is some critical point. Exactly at the critical point, the energy growth rate will jump to some universal value, as I show you. And between the peaks, we have perfectly insulating phase. And this was fully confirmed by numerical simulations. And you see that the critical values are actually quite close to the numerical simulations. So furthermore, if you remember in the usual kick rotor, as I already explained you a moment ago, the free rotation will parallel law similar to the parallel law of the disorders. And then let's try to change the disorder a little bit. How can we change the disorder? We don't have disorder at all. And the idea is to change the power of this dispersion from 2 to 4 or absolute or some really generic value. And then we compare the results for these two different powers. You see actually also many other powers. We see the peak is almost the same, okay? So there is no difference at all. So this means that the simulation results, as we expect, are really robust against the change of the free rotation, something similar to disorders. And then, you know, in this system, there is kind of isotopicity, and therefore we take this into account, and we can calculate the critical diffusion coefficient explicitly with two kinds of potential. Then you see they are really close to each other, and it's like a 0.25. So this is slightly larger because for the topic is in the deeper semi-classical regime, we cannot go to much longer time. So a moment ago, I changed the free rotation, namely the disorders, and now I will change the kicking potential and see what happens. So to be specific, now I change this parameter mu. A moment ago it's 1, now I would like to change this mu, and then we end up with this phase diagram. So you can see the critical, the phase boundary is an excellent agreement with the phase boundary given by the analytical theory. Now, in this diagram, we change mu, and change 1 over h bar. So we get this diagram. And we fix, now if we change the power simultaneously, what happens? This means we change the disorders again. You see the two phase diagrams, there are not so much difference, okay? Again, the phase diagram is really robust. So basically, it's a very good signature of the topological phenomena, even we just stick to the numerical results. Now, what's the physical reason behind? Let's consider some interesting case. To understand some to get some insight into this phenomena, let's try to change the system a little bit. Now, I will fix everything except they are allowed this additional frequency to be commensurate with 2 pi. Okay? So I just change this. So what happens? According to the analytical theory, the system, because now the system is periodic in the virtual angular momentum space chronically conjugate to the quasi-periodic driving, the topology is given by the first homotopical group, which turns out to be trivial. Okay, there is no topological phenomena. And then, indeed, if we reproduce the calculations, we see that there is no topological term in the action. And basically now, the action is only controlled by the single parameter EQ. This is basically the rescaled energy growth within a single period, because now the system is time period, perfectly time periodic. And then, according to this theory, we can predict analytically that in the long time, the energy will saturate like a typical, like a usual dynamic localization, and then it is given by this value. Okay. Now, indeed, this scaling is in perfect agreement with numerical simulations. Moreover, we also run the simulations for this rational value of omega theta divided by 2 pi. Now, the result is following. So, you see, if this ratio is irrational, and this h bar is a critical value, as we said, it's a mathematical phase, and it's given by this linear diffusion. Now, if I approximate this irrational number by this rational number, we see after a long time, so instead of a critical diffusion, we always have the saturation, okay, dynamic localization. And then the localization time increased monotonically with the denominator. This means that all the topology, all these finding phenomena disappeared. We just find the dynamic localization as usual. And what happens behind? So we check the kinetic, we check the motion in both the real angular momentum space N1 and also the virtual angular momentum space N2. Now you see what happens. So in a long time, the motion in the angular momentum, in the virtual angular momentum space actually is ballistic. This means that the system actually is no longer chaotic, at least in some directions. And as long as this happens, so the topological phenomena disappear. So I have 15 minutes left. So now I will introduce to you a connection between this formula, between this phenomena and the Haldane conjecture for quantum antiferromagnetic chain. So what is Haldane conjecture? So basically, the model is following. So I have a one-dimensional lattice. At each lattice, there is a quantum spin, S, and the nearest spin is coupled to each other while the antiferromagnetic exchange interaction. So, and now the question is that this is a quantum spin, and then we would like to understand what's the property at the long range of the quantum ground state. And this answer, this was conjectured by Haldane in 1983. Basically, the result is following. It turns out that it depends on the quantum spin. If the spin is an integer, it turns out that the spins will have the short-range correlation in the ground state. And this means that if the two spins are really far away from each other, they do not talk to each other, and as a result, we have the disorder phase. Now, if the system is a high integer spin, what happens? The story is totally changed. It turns out that even two spins are really far away from each other, they are still correlated. And he followed conjecture that this system is actually at a critical phase. Okay? Now, how Haldane come up with this conjecture? So I would not like to explain all the details, but basically the scenario is following. Let's use the Schwinger-Wigner representation for the quantum spin. Okay? And then basically this spin is parameterized by the angle theta and psi, which is the same angle parameterizing the two spheres. And then after this Schwinger-Wigner representation, we have the path integral representation for a partition function, which is the following. It is just the integral over functional integral over these two angles. So, in the next step, he would like to decompose the spin into two parts, which are canonical, which are orthogonal to each other. And the first term is at the end, is basically the local orientation of the layer magnetization. And the second part is the quantum field, basically is the local fluctuations orthogonal to the local layer magnetization. And then, after this decomposition, he managed to express in terms of the function, the partition function, in terms of the functional integral over these two fields. Okay, and the result is following. Sorry, there is some typo. This includes dx d tau also. So this is the action after this decomposition. So basically, the first term describes the stiffness of the spin wave, and the second part basically is the describe the transverse magnetic susceptibility. And this term, as I will show you later on, more or less is already topological because it is invariant when we change the metric of the 1+1 space-time. Indeed, if we integrate out the L field, what do we get? After rescaling, we get this result. So it includes the two terms. The first term will describe the spin wave, and how the spin wave propagates in space-time, and it is contributed. And whether it is easy to propagate or not is dominated by this coupling constant. Okay, and then the second term is the topological term. Okay, and then actually this term is the coefficient is controlled by the spin, which is the quantized theta angle. Now, what does this model mean? Haldane realized the following. So, because we have this mathematical identity, basically this is the winding number for the map from the two sphere to another two sphere. Okay, this is the winding number, and as a result, we have this one. Now, because of this identity, it turns out that the partition function can be expressed as the contributions of different setters. Okay? Okay. Have different setters. So, and now, if S is integer, it turns out that all the setters we contribute, we add constructively to each color, and as a result, the coupling constant will be normalized to infinite. This means that the waves, the spin wave, cannot be propagated for a long time, and as a result, we have the disordered phase. Now, if it is a hard integer spin, what happens? So it turns out that all the contributions from different centers will destructively add to each color, and as a result, the coupling constant will be renormalized to some final value, and this is the critical phase. So in this slide, I have only one slide, two slides left. So how can we see Haldane conjecture from this kick spin one-half rotor? So actually, what is important with this topology is the compact part, the two sphere. The two sphere can be parameterized by this in this way, and as a result, when we substitute this into that, we get this model. So you see, this sigma h will press the law of the spin. And in the two angular momentum space, we press the law of the space-time. So then as a result, what is this? We see this insulating phase in the kick rotor of spin one-half is similar to the quantum antiferromagnetic chain in the disordered phase. And this integer number, integer Hall conductivity will press the law similar to the integer spin. And for the peak, because it is quantized a high integer, and this press the law of the high integer spin in the quantum antiferromagnetic chain. And as a result, indeed, in this case, we also have the critical phase, the same as Haldane's conjecture. Very excellent question. Very excellent question. So, of course, I studied, this is something why I so enthusiastic at this problem. So the question is that, the point is that this kick rotor is different from the disordered system in the following sense. So because, if you consider the usual disordered systems, so in order to get this sigma model, this target space, we know we need to have a main field approximation. But if we are in a strongly coupled limit, as you studied also for 1D, this target space will be totally changed. And then what happens, exactly speaking, the